Alharfouch, and I'm starting my first PhD in Hidayah Sisik. And yeah, as Dr. Martin said, my supervisor are Juan Hidalgo and Jerome from Hidayah. And we are, well, today I will, since it's the first time I present here, I will just show you one part of my PhD, which is water uptake dynamics under Mediterranean climates. That's based on our field data. And in CSIC, I work with two research groups, which is the idea of the PhD, that the field work, we do it with Dr. Jerome and Dr. Pilar, where we have a field experiment. And then from that, we also work with modeling team, with Dr. Juan Hidalgo, to model what we see in the field. And so the motivation behind the work is that the drastic changes that we are witnessing in the temperature and precipitation in the Mediterranean. So according to the IPCC report of 2022, they predicted that we might have a decrease up to 10 to 30% in precipitation, with of course increasing global warming levels. But it's also, for the temperature, it's almost certain that we will have also an increase up to 20% in the global warming. So for this, we really need to understand how this will affect our plant and soil system, which is an essential zone system in our world. So, and to begin with, this system is very complex. It has a lot of elements and processes that process multiple fields of science. And usually the common practice is that each element or each process, they study it separately in each field. So, but the problem is that these processes and these elements are interconnected, they affect each other. So we need a more cross-disciplinary approach. And by cross-disciplinary approach, we would like to see that we have field work, and we have we want to include also the isotope hydrology, which is a process that helps us to trace the water movement in this zone, and also include a modeling element to this. And in this, we have very rare publication in this, only this in the 2022 that actually combine all these three fields, let's say, but in a very controlled environment. So it's not also in a field, more experimental. And so with this, if we have this cross-disciplinary approach, we may have a better understanding of the water distribution in this system, and then we will have a better action and adaptation methods for, you know, our scarce water source resources. And also for the objective, well, the main objective of the work, the big main objective is that we would like to understand the water, understand the water subsurface mixing and the soil-plant interaction better. And for this talk, I will just talk about the first part of the work, is that how, with high resolution and comprehensive data set, we can enhance our understanding of this water uptake by the trees under different wetness conditions. And to make it simple, we want to see what they do, the trees, when they are, when the situation is dry. And for this, the methodology, also this is like the, the whole methodology of the PhD, where we want, the idea is that we want to combine hydrological field data and stable water isotopes in an integrated flow and transport model. So we have two parts, the field experiment and the numerical model part. But for now, in this talk, I will focus on the field experiment and what we actually got from it. And so for the field experiment, we designed this setup where we have a meteorological station where we monitor data like the rainfall, the wind speed, the net radiation, and the temperature on like 5-minute intervals. We have these data. And we started the monitoring system from May to October of 2022, and it's still ongoing, but for now I'll show you this specific months. And we also, to have an idea of the source to the soil hydrometric situation, we have installed in different places, in different depth, soil water content and soil water potential proofs. And also for the tree, to have a better understanding of the tree drinking behavior, we have a dendrometer, which is an instrument that can help you. It tracks the swelling and the shrinking of the tree, and which give us an indication of the growth of the trees, and also how they are, let's say, transpiring. But for transpiration or for the flow, exactly, we have the sensors of the sap flow sensor, it's called. And of course, again, it's an instrument that helps us. It's basically 2 needles injected in the tree, and one is heated and one is not heated. And so by this, you give it always it's always fed with electricity or voltage. So you get a voltage difference every time. And with that, you can understand when the water is actually going up the tree, it can record it. And we have from this something called sap flow rate. And again, all of these, we have them at 5 minutes intervals for the whole day. And so for the result, we did that experiment in Valsebra research catchment with the field group. And Valsebra basically is a mountain area, a village that is 100 kilometers north of Barcelona, and it's located in the headwater of the Llobregat River. And the climate there is characterized as humid Mediterranean. And we have an historical mean of precipitation in that area that is 880 millimeters, but in the last 3 years it declined to 600. So we have 25% and an annual temperature of 9.8, but then it also increased in the last 3 years of 10% to 10.8. So we are already, even if it's a short 3 years, we cannot say it for certain, but we are heading the way that IPCC is predicting. And the experiment, exactly, we did it in a small plot that is less than 200 meters square. And we experimented on 6 Scots pine trees. We have the instrument of sap flow and then the meter on 6 of them. And for the result, so first I will show you the traditional way of tree physiologists, how they try to understand the tree behavior, and that's by relating it to the atmospheric condition. And so here I show you the time series from May to October of the sap flow rates, which is basically means how much water is the tree drinking liter per day in this situation. And the rainfall, I don't know if you can see the volumes of the rain, and the rainfall amounts at all of this period. And and for the atmospheric condition, we show it by something called vapor pressure deficit. And this it's a variable that you calculate from temperature and net radiation, and it tells you from relative humidity and temperature. And this basically, it tells you the atmospheric demand from the trees or from the plants in general to start to transpire and give it water. So it tells you as well, like it goes from 0 up to whatever, SVBD in kilopascal. And it's, the low means that it's humid, the weather, and then when it's higher, it means that it's drier and drier. So we are in summer, we should have higher VBTs. And so if we look at this, the first thing, the sap flow, we can see that in general, on average, the sap flow, the trees are drinking almost like 20 liters of water per day. And that's like not so little amount. And second is that we see that indeed there's some clear correlation between the tree behavior and the atmosphere. So we see that when there is a high demand from the atmosphere for the tree to start to transpire and drink, they are actually drinking. But then when it's low, when it's humid and there is rain, they stop drinking. And however, we see here in the month of July, which was our driest month and the hottest month, we see here the demand is super high, but for some reason, the trees are not actually transparent. Actually, they are declining, so they are not answering to this atmospheric demand. And this is a bit weird because, well, first they say the tree physiologist says here that some of the plants, in general, when the VPD is very high, which is maybe above 1.5 kilopascal, the plants have like a defense mechanism where they close their pores, so they stop transpiring the water. So this could be the reason, but then, since it's very high here, the VPD. But the issue here is we see that here it's even higher, but the trees are transpiring. So then that's not the situation. So for this, we need to look to more data to see what's happening in these situations. And first, we can see more of the variables from the tree that we can get. There, from the dendrometer, we can get a variable that is called tree water deficit. And this tree water deficit is something that, of course, it's empirical, and it tells you that, so we have a tree, and it has a maximum capacity of taking up water, cannot take more than 20 liters per day, let's say. And the tree water deficit is that we have the maximum and the actual tree drinking uptaking that is at that moment, let's say. And so it's the difference between the maximum and the optimum. And then it tells you how stressed the tree is. So when we have a maximum of 20 and then it takes 1 only, so we have a 19 point of difference that it cannot answer for that. So then it's more stressed. And indeed, we see here that in this month, they are not answering to the atmosphere, so they are the most stressed. And here, when they had also high demand, but they were actually answering and they did not have a deficit. So what is the reason? It's absolutely not, it's not the fact that they are closing their pores, there is another reason. And that reason we can see it by looking at the soil. Do we have water in the soil? So, and that we present this thing by the soil water potential, which is basically the metric pressure. The metric pressure in the soil, which tells you how we have water or we don't have water, but the water that we have, is it actually available for the tree to uptake or not? And we have it from the field in kilopascal, but to present it, because it can range from like in 3 or 4 order of magnitude or even more, so it will not show fluctuation if we show it in kilopascal. That's why we do the log 10 of the absolute value, and then it's called the BF, and it ranges from also 0 to 4 or wherever it is, and the higher it is, the drier the soil means. The drier the soil, or it doesn't have to be even dry. It means that the water is not available for the tree to uptake, because there is a certain point where the water can be taken by the trees, and which is beyond the field capacity, they call it, and so we see here that in this month, here we have the soil water potential is at its highest. So meaning the soil is super dry, and the trees cannot take the water. So there is no water actually to uptake. So that is why they are stressed. That's why they cannot answer for the demand. And in this part where the demand was high, we still see that there is actually water for the trees to take, and they are transpiring just fine. So we see that there is this interplay. Another thing as well, that here at 4.0 pF, 4.2 pF, it's called the wilting point. It's a general or standard, let's say, value that they say at this point, when the soil water reaches this point, the tree or the plants in general cannot take the water because there is no water. But then if it rains, they say that then it will not even be able, that the trees or the roots are dead. They cannot take the water anymore. So it's like, that's why it's called the wilting points, the point where they start to wilt and they cannot answer even if there is rain. However, in our situation for our trees, the Scots pine, they show that they are very resilient to drought and they can sustain this drought behavior. So when we had a huge rain, which is almost 60 millimeter, just on the 31st of July, the soil potential dropped down, means that the soil is rewetting, and then the deficit is then at minimum, and then the tree started to transpire, and everything is fine. So it did not die, luckily. And so we see finally that here we have this interplay between the atmospheric demand and the soil, the water in the soil. And we see here, I present the sap flow rate in liter per hour against the vapor pressure deficit. And we see that and the color scale is the soil water potential. As the lighter it goes, the drier it is, the soil. And indeed, we see at the beginning, the trees transpire more and more with more VVDs until it plateaus at a certain point, which is more or less between 1.5 and 2.5, which is the optimal range of the transpiration. And we see that the maximum is that they are transpiring 3.5 liters per day. And but then here we see that even though we have high water, like the water is available in the soil, but the vapor pressure, the atmospheric demand is very low, so they don't do anything, they don't transpire. But here we see that there is high demand, but again, they are not transpiring because there is no water in the soil. So we see that there is this close relation between the two elements for the tree to start to take up the water. And so finally, we see that by this comprehensive data set from different point of view, from the atmosphere, the trees, the soil, we can learn a lot about, or more, let's say, about the drinking behavior of the trees and their uptake and their dynamics more in deep interpretation. And so for me, this data would be input data more or less for the model that I will create. And but for now, we're still working on that because we need more work on this, mixing models and these kind of things. And then we will start this year soon. We'll start with an American model. And thank you. And sorry, I know it's very strange topic for you, maybe at the UPC. And thanks.
As you mentioned, really interesting presentation and really good job. I was curious about what were the criteria to select the kind of trees that you're using in this experimental site, because you mentioned that they are resistant to the drought periods. So this was a consideration previously, or it was something that you discovered in the middle of the experiment?
Exactly. So the thing is that in Valsevic catchment in particular, or in general in any Mediterranean catchment, Scots pine are not the main trees. Scots pine are more in the Scandinavian countries and in higher altitudes. But this area especially, it was in before the 60s, it was terraced for agricultural use. And then the terraced were abandoned, and then there was a forestation with Scots pine out of nowhere. They just come out as Scots pine. Before that, they were let's say the historic forest was oaks. And now it's Scots pine. So the majority now is Scots pine. That's why we started to study them. And as you said, later we found that they are actually more resilient to drought than any other tree. So it's very interesting actually, so that we can, it can be an indication for forest management that we can think of growing more Scots pine in respect to other trees that they cannot actually sustain droughts.
Okay, because following your explanation, I understand that when we're constructing many dams here, they were filling with this specific kind of tree without the knowledge that
Yeah.
what will be the consequences of this kind of,
Yeah,
because the previous ones were deforested by the construction, so
okay, yeah.
I don't know if these have, I think that it's a close relationship between the kind of trees that you have and the type of soil that will be produced in the first shape. Maybe because you were mentioning this
Yeah.
thing in the soil that maybe some answers would be in that one, but I'm not
Yes.
sure.
Yeah, would be actually, this is very interesting. But these trees are also, they are not among the ones that don't drink a lot, like they drink 20 liter. Some trees actually drink 2,000 and even more per day. So these are one of, let's say, the economic one. And they just sustain the drought.
And these are research funds, I think, so for the aquifers or some kind of systems that are in the mountains, I don't know. In this, because this is the beginning of headwaters of the Llobregat River,
Yes,
so are
exactly,
you?
yes. So yeah, this is basically the whole catchment. And what the highlighted is what we are monitoring and studying on daily basis. And well, here is my plot, but yeah, in general, this is the catchment, and it's full of, it was terraced, most of it. And now it's full of oaks, Scots pine, and some other small bushes that,
These have some snow periods, you know.
very little, but yeah.
Okay.
Yeah.
So, but the research is something that you have to evaluate in the
Yeah,
research,
yeah, of
to do
course.
some kind of,
Water
know,
patterns, of course.
I have one question. I think in slide 8 and 9 we talk about reaching point.
Yeah.
I have a question. So you said it's not completely dry, there is still water in the soil.
Could be. No,
The trees cannot take water.
exactly, because, for the tree to take, also here, I'm not sure, there is here at 1.5 something called the field capacity. And so basically the field capacity, well, let's say it rains, so the whole water, the soil is saturated, it's full, it's on zero soil water potential. And then here you can, the plants does not take the water, even though they are uptake and should show.
And the reason is because they are trapped in the pores.
Exactly. So you see the roots of even though this is an illustration, but the roots of the tree is just up the groundwater level. They do not go to the saturation part because they need some oxygen to, give and take the water. It's like to create pressure so that they can take out the water. So when it's fully saturated, they cannot take the water. And you see that here, for example. Here, it's fully saturated. They are stressed. They are taking. Here, exactly. They are not taking the water as much. So so they need some. How can I say? There is what they call a level of water availability for the plant, and that is between 1.5 and 4.2. But these numbers it depends on each type of plant. It's different. The 1.5 you reach it after 3 or 4 days after the wetting period, the first wetting period, because the first water goes down by drainage due to gravity. So they go to groundwater or the streams or whatever. So this is not like they are the fast moving water they call them. And then the water that stays in the soil, this is what the trees start to take. But if let's say they are start to taking the pores that we are covered with the films of water, as they start to take and take and take, the films start to be like thinner, and then it breaks. So there is no there is oxygen more or air, let's say, more than the water itself. So then the tree cannot take this anymore because they need the suction of them cannot exceed that much. And then they get to this point where it's like around, in kilopascal, let's say it's around 2,500 or even more, a little bit, kilopascal. So this they cannot, it's their limit, they cannot do any more suction like that. And then they stop, they just cannot.
Okay, I have a question on I don't know, it's a comment,
Yeah.
because this set flow,
Yeah.
can you relate it to evapotranspiration?
Yeah, of course.
And also, because typically, the typical thing that you do is to calculate the reference heat
Yes.
for transpiration.
Exactly.
And
Yeah.
montes or something.
Yeah.
You
Exactly.
did?
Yeah. And so the thing is with the sap flow, it's exactly the flow of, just an indication of the flow of water in the tree, not outside, right?
Yeah.
But with some kind of an approximation, and also this is on a tree level. The transpiration on the evapotranspiration is calculated on more than one tree, of course, and it needs the area. It needs it usually what you do to transfer from sap flow to transpiration is that you need how many actually leaves are transferred, every area of every leaf, but there's some kind of approximation where you can just like the whole canopy, you can approximate it to a certain area, and then you calculate the transpiration based on that, and we are.
Because you can, but that is, let's say, a reference or a potential.
This is the
It's
actual.
the maximum.
Exactly. This is the actual. The reference would be from our meteorological.
And there are different ways, there are very simple ways.
Yeah.
You only need a minimum and maximum input
Yeah.
or something.
Exactly.
Or
Yeah. It's
as a
with the
multi,
motif equation. Yeah.
And typically, you would have a higher value in summer.
Yeah, exactly. Yeah.
It also depends on the vapor pressure.
Yeah. Yeah. Exactly.
Because that to me would be the most important, more important than the vapor pressure deficit, I would say.
Okay. Yeah.
Because it is a sort of maximum.
Yeah,
It reflects a maximum.
Yeah.
Set
The need. Yeah. Exactly. Yeah.
Of course, if they are stressed, because they make it open,
Yeah. Yeah.
because there's no water, then
Mm.
you don't have any stress.
Yeah. Yeah. True.
But I typically use some kind of means to means or some kind of relation to
yeah.
calculate the
Yeah, yeah.
evapotranspiration.
Yeah, of
Maybe to
course.
value extra data if it's very simple.
Yeah. Of course, that is only going still like this is more. That's not that advanced, so still in preliminary. So we more of mixing these models and GIS and yeah.
Yes, because this is not that big that big.
No, it's small. Yeah, but
It's, that's quite big.
200. Yeah.
I don't know, GIS, well, if you want to upscale, maybe interesting.
Yeah.
Because I saw those some it wasn't sure.
More questions?
And also, can you provide some guidance for farmers?
Yeah.
According to
Farmers.
that's, can you provide some guidance to how to pour water to increase the production of farm?
Of farm. Okay. Well, then. I mean, for farmers, we will need to study the kind of plant they are growing first, because it will be completely different kind of transpiration and all this. It's different, but this is for more forest management and water resource management. It's not farming. And so for the forest, because sometimes there is, especially in the Valsepra, because it was grown spontaneously. So there was not management at all. You see that if we go there, and by the way, my field supervisor told me if anyone interested to go to Valsepra, just tell us and we can take you there. And so in that area, the trees are either very dense, like I don't know, you can see 100 trees in just like a few meters, and or they are very scarce. And so the trees that are very dense, they are small trees, like not small, but they cannot actually grow. So their diameter is super small, and they don't help anyone. They don't help the environment, and they don't help themselves. And they are just taking water and being small. So the idea is that for the forest management is that it's okay to cut some trees. It's part of the management, and then you can replant trees in different area that needs trees and these kind of things. So this is the kind of thing that maybe come from part of the PhD. Yeah.
the behavior of tree uptaking, he considers the how can I say, the size of the tree?
Yeah, of
Or
course.
maybe the more, like the tiny trees uptaking more water or?
No,
or-
yeah, actually there is, it's not linear, but there is the bigger trees transpire more, take water more than the smaller trees. And like when the tree that we chose, the 6 trees are more or less the same diameter, but there is like the smallest one we have, it's like 12 centimeter in diameter, and the biggest one is double that size. And we see almost more than double the uptake of the bigger tree. So yeah, it is correlated, and it's actually integrated in here because they say what you get first is sap flow density. It's called, and this does not include the area of the area of the tree that is actually transpiring water, because it's not the whole section of the tree does not take the whole water. It's part of that section. And so in the sap flow rate, you include you like divide the sap flow density by the area that is actually taking the water. So in this we have like it is included. That's why also you see a lot of differences. Like this is I don't know if you can see it actually, but the dark line is the mean value of the 6 trees, and there is a highlighted envelope. There is, maybe you cannot see it, but it's the standard deviation among the trees.
Okay, more questions? No? Then, thank you.
Thank you.
I have another question to online audience. So, any questions from the online audience? No? No, then we
Okay, thank you.
Okay. Okay, bye bye.